my dear students, welcome to our channel MS2 Physics, where physics gets charged. In the previous videos we had derived the expression for magnetic field induction due to current carrying circular wire by using Biot-Savart law and its various applications we have discussed, right? So now again by using the same Biot-Savart law, we are going to derive the expression for magnetic field due to a long straight current carrying conductor. So in this here I am taking, this is a one long straight conductor which carries the current I. So when the current is flows in upward direction supposed to be, so that to know the direction of generating magnetic field here I am using right hand thumb rule. So when you are stretching the thumbprint in the direction of current, so that the curling fingers are giving the direction of generating magnetic field here, my tip of the fingers are goes inside. So as our intention is to find the expression for magnetic field at a point P, which is at the distance d from this current carrying conductor. So at this point that generated magnetic field is inward, right? So here we got the direction here. Now we are going to derive the expression for this, and as the length is continuously right from lower end to top end, so it is not possible to write directly mu naught I L sin theta by r square if you are supposing L is the length of the conductor. So for that it is a continuous distribution, right? So for every part of the conductor around it magnetic field is generated. So for that I am consider one small element of this wire, okay, of length dy, which is at the distance of y from the midpoint or center of this conductor. And we are going to find the magnetic field at a point P at the distance d from this. So when you are joining the line from this element dy to this point P, so it will make certain angle theta. So according to Biot-Savart, this theta gives the angle between the direction of current element and the position vector r. Okay, and here in this case we can write the magnetic field at this point P due to the small element dy is the supposed to be dB. The dB is actually from Biot-Savart law we have mu naught by 4 pi IDL sin theta by r square. So that mu naught by 4 pi I dl, length of the element, I am supposing the length of the element is dy, into sin theta, here angle made by this element with the position vector is theta, by r square. So here this line joining with a point P to this element with a normal will make certain angle, that angle I am supposing pi. So that can I write this theta as 90 minus pi? Why? Because this point is at perpendicular distance from the conductor. So when this is a theta, here is a 90, it is theta 90, this is a pi. So theta can be written as a 90 minus pi. So that here mu naught by 4 pi, we can write I dy sin 90 minus pi by r square. So why I am writing this expression in terms of pi is because of when this length of the element increases or goes down from the mid or downwards or upwards, this pi is varies. Pi is varies right from lower end of the conductor to top end of the conductor, that pi is varies here. So that here we will get dp is equals to mu naught I by 4 pi of I already written. So I dy cos pi by r square. Let this is the equation 1 here. Okay. So now here from this figure can I write a tan pi is equals to to this pi, opposite side is this and adjacent side is here, so that we can write a y by d. This implies we can write y is equals to d tan pi. On differentiating above equation, so that here we will get a dy is equals to d into differentiation of tan pi is what? Secant square pi into d pi. Why? Because dy by d pi, I am sending d pi to that side. So I will get dy is equals to d into secant square pi d pi is the value of dy. Let this is the equation 2. Again from the same figure, if you want to write the secant pi is the hypotenuse by adjacent side, so that you will get r by d. So by this R is equals to D into secant pi. Let this is the equation 3. So now on substituting equation 2 and 3 in a 1, 2 and 3 in a 1, so that we will get here from the first equation dB is equals to mu naught I by 4 pi dy. The value of dy can be written as a from here second equation d into secant square pi, okay, into d pi into cos pi according to the first equation upon r square. R square is d secant pi, so that you will get a d square secant square pi here. Okay, so that here we can write dB is equals to mu naught I by 4 pi. One dd get cancelled, one more d is there, secant square pi is get cancelled, so we will get a cos pi into d pi. Let this is the equation number 4. So here this is the expression for magnetic field induction at a point P due to the small element of length dy of the current carrying wire, but our intention is to find the total magnetic field produced at a point P due to entire length of the conductor. So that we can obtain on integrating this equation from the limits from lower end to top end here, means on integrating above equation within its proper limits, we will get the total magnetic field induction here. So on integrating the previous equation, we will get integral dB is equals to mu naught I by 4 pi d of integral cos pi into d pi. So in this expression, the variable is the pi. Pi is the angle made by the position vector right from point to the element. This element length is varies right from lower end to the top end. So when you are joining the lower end to this point P, here this is the angle, and when you are joining from point to the top end, so here we will get the another angle. Let this angle is supposed to be alpha, and this total angle is said to be beta here, means pi is varies from bottom angle pi beta to the top angle alpha, and here always we are going from axis to that line to get the angle. So means here to get the alpha we are moving in the clockwise, to get the beta we are moving in the anti-clockwise. So according to basics of trigonometry, the anti-clockwise is taken to be negative angle and the clockwise is taken to be positive angle. Got my point how I am taking the units here, students? So now integral dB is the P. So this is equals to mu naught I by 4 pi d of cos pi is, integral cos pi is what? Sin pi of the limits minus beta to alpha. So therefore B is equals to mu naught I by 4 pi d of, you can write a upper limit minus lower limit, means wherever the pi is there, that you have to substitute the upper limit, minus at the place of pi you have to substitute a minus beta. And again from basics of trigonometry we know sine of minus theta is the minus sine theta, so that this expression will become B is equals to mu naught I by 4 pi d of sine alpha plus sine beta. This is what the expression for the magnetic field induction due to entire conductor of length L at a certain perpendicular distance d here. So this alpha and beta are what? The angles made by the ends, the line joining from ends to the point with a normal to the otherwise with a perpendicular distance of that point from the current carrying conductor. Sir, in the problems if they are given, instead of given alpha beta, if they are given the angles made by the conductor with those position vectors, means these two, means these two, let here it is said to be theta 1 and here it is said to be theta 2. So from this figure, if you are observing here, this is a right angle triangle. So theta 2 alpha can write as sine 90 minus theta 2, and this beta can write as 90 minus theta 1. So that sine 90 minus theta 1 is a cos theta 1, sine 90 minus theta 2 is a cos theta 2. Therefore, we can also be write this B is equals to mu naught I by 4 pi d of cos theta 1 plus cos theta 2. Here theta 1, theta 2 are the angles made by the conductor with a position vector which are joining from point to the two ends of the conductor, right? So now the important thing is, while you are taking the applications, now we'll discuss some applications here. So better to, for especially for NEET students, if you are remembering this expression to find the magnetic field induction at anywhere or any case is enough. I am giving the derivation especially for mains and advanced students. Why? Because when you are doing this such kind of derivations here, the knowledge of derivation of this by using integration is helpful in the level of advanced level problems. So right, so when you are coming to the NEET students, you should be start the preparation from here, please. Because this is the expression for the magnetic field induction due to long straight current carrying conductor is mu naught I by 4 pi d of sin alpha plus sin beta when the angles are given at the position vectors. If they are given with respect to the conductor, then you have to take cos theta 1 plus cos theta 2 into mu naught I by 4 pi d here. Sir, so this is what we are taking certain length, means there are number of possible cases that both the ends are infinite, or one end is finite, another end is infinite, or the point is at the base of one end and another is infinite, or the length of the wire is finite and it is at a midpoint. So these all are the probable cases which we are arising the questions. While designing the questions, these are the probable cases. Now we will discuss one after the other. As we got the expression for B due to a long straight wire is mu naught I by 4 pi d of sin alpha plus sin beta. So now taking the cases is that first is of infinite length, means both the ends of the wire are infinite and the point is at a distance d from the center. So alpha beta are the angles made by the line joining from ends to this point P. So when you are joining the lines as it infinite, so that those lines are perpendicular to this line OP. So alpha and beta both are equal and that should be of 90 degrees. When it is of 90 degrees, so that we can write B at this point is equals to mu naught I by 4 pi d of sin alpha plus sin beta is sin 90 plus sin 90. So sin 90 is a 1, 1 plus 1 is a 2, so that mu naught I by 4 pi d of 1 plus 1. So we will get the expression for B due to this infinite length conductor is mu naught I by 2 pi d is the expression. Means wherever the straight wire is of infinite length, simply at any distance d, the magnetic field is what? Mu naught I by 2 pi d here, right? So now, and the current is in upward direction, so the magnetic field is into the plane of the paper. So now in the second case, we are taking the wire of one end is finite, another end is infinite, and that point is lies at this point. So always the line joining from end to that point with a normal is the angle alpha. So by this here we can write alpha is equals to 90 degrees and beta is equals to 0 degrees. So that by using the expression B is equals to mu naught I by 4 pi d of sin 90 plus sin 0 here. So sin 0 is a 0, sin 90 is a 1. So that the expression for B due to one end of the conductor which is of finite length, another end is infinite, is B is equals to mu naught I by 4 pi d. And if you are taking the current direction is downwards, supposed to be, so now stretch the thumbprint is in downwards, so that my tip of the curling fingers are out of the plane of the paper, which are coming away from the plane of the board. So away from the plane of the board is denoted by dot, into the plane of the board is denoted by into mark. We are discussing the previous videos, right? So now this is the way we can find the magnetic field due to infinite length of the conductor and semi-infinite, means one end is finite, another end is infinite. So now we are coming to this third case is a finite length only, whose length is supposed to be L, so that at the perpendicular bisector, means this part of the wire is L by 2 and the upper part is also of L by 2. So when these two lengths are equal and this D, so this alpha and beta are also be equal. When they are equal, so we can write the expression for B as mu naught I by 4 pi D of either you may write sin alpha plus sin alpha, or you may write sin beta plus sin beta here, so that here we can write B is equals to mu naught I by 4 pi D of 2 sin alpha. This is the way we can write the expression for the magnetic field induction due to finite length of the conductor here. So now my point is, sir, alpha is not given. Alpha is not given. They are given D and L by 2. Then how we could write, sir? So from this we can write sin alpha is equals to opposite by adjacent hypotenuse, means L by 2 by hypotenuse is what you can write under root of L by 2 whole square plus D square. So L square plus 4D square upon 2 is the sin alpha here. So that can I write directly L by 2 by under root of L square plus 4D square by 2. This 2 get cancelled. When 2 get cancelled, so we can write the expression for B as mu naught I by 4 pi D of 2 times of L by under root of L square plus 4D square. If they are given the length of the conductor, you may use this equation. If length is not given, just angle is known. So then by using this, we can find the magnitude of magnetic induction due to this conductor. So now another important case is the fourth case here. If you are taking the current carrying conductor like this and carries the current here. So now if you are taking whether it is a finite or infinite place, if we are taking the point P which lies along the length of the conductor, not on the conductor, please, the point lies along the conductor, then what should be the theta here? Theta is either 0 degrees or 180 degrees. When it is 0 or 180 degrees, so that the B will become 0 here. B is equals to 0. Why? Because from Bayat Sevatla, B is equals to mu naught by 4 pi I dl sin theta by r square, or I dl bar cross r bar. Here dl bar and r bar both are parallel to each other or anti-parallel. So when for anti-parallel parallel vectors, the cross product is 0. When the cross product is 0, we have here from Bayat Sevatla mu naught by 4 pi I into dl bar cross r bar by r cube, isn't it? When length of the element of the conductor and the radius vector both are along the same direction, so cross product of these two parallel or anti-parallel vector is 0. So that you should keep in mind that this is a very important one. Whenever the point lies along the length of the conductor, the magnetic field induction at that point is 0. So based on these 4 important cases, we can find the magnetic field due to any shape of the any type of the conductor which should be of straight end. When it is a straight end of finite or infinite, one end is finite, another is infinite, or both the ends are finite. Based on this, if you are thorough with this, then you can solve the problem based on this of any type. So that we will solve the problems based on this in our next video, but you focus on the first basic equation is that magnetic field due to that infinite length of the conductor is what? Mu naught I by 4 pi D of sin alpha plus sin beta. After that, these expressions, especially for NEET students, please. So whenever coming to the mains and advanced students, please go through that derivation also, which is very helpful in solving the higher models of problems which are suitable for tough models of mains or advanced. Thank you students, thank you for watching. If you like my videos, do like, share, comment and subscribe my channel to get latest videos.